Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from integrals, right? So in this lecture we are going to solve this important integral which is from 0 to 1, and the integrand is log x raised to n, where this n is a natural number, right? So n belongs to the set of natural numbers, and here we have logarithm of x, and here log x is the natural log, that is with base e, right? So we can also write log of x as ln x, right? But we'll prefer this notation, right? So let us start and let us see how we can solve this important integral with the help of gamma functions. So let us take this integral as I, right? And let us make the substitution as y is equal to a log of x, right? So when we take y is equal to log of x, it implies that x is equal to e raised to y, right? Okay, now if we differentiate x with respect to y, then we have dx over dy is equal to e raised to y, right? Because the derivative of e raised to y with respect to y is e raised to y. So now we have dx is equal to e raised to y dy, right? So for this dx we have e raised to y dy, right? Now here the limits vary from 0 to 1, right? So when we have the lower limit as x is equal to 0, then the value of y can be obtained by taking x is equal to 0 in this relation. So when x is equal to 0, then y is equal to a log of 0, right? And log of 0, it tends to minus infinity, right? And similarly here when we take x is equal to 1, then y is equal to log of 1. So we have here log of 1 is equal to 0, right? So when x goes from 0 to 1, then y goes from minus infinity to 0, right? So now we can write this integral I in terms of y as minus infinity to 0. Then log x is replaced by y, so we have y raised to n, and dx is e raised to y dy, right? So now we have this integral, right? Now to move further, what we will do, we'll again make use of the method of substitution, right? So let us further substitute y is equal to say minus t, right? So when we take y is equal to minus t, then here we have e raised to minus t, right? So why we are making this substitution? Because we want to convert this integral into gamma function, right? So we have to take here y is equal to minus t. So dy is equal to minus dt, right? And let us change the limits accordingly, right? So here see y varies from minus infinity to 0. So now let us take t is equal to minus y, right? So when y is equal to minus infinity, or in other words, we can say that when y tends to minus infinity, then t tends to negative of infinity, because here we'll take y is equal to minus infinity, so that is positive infinity, right? So when y tends to minus infinity, then t tends to infinity. And similarly, when y is equal to 0, then obviously t is equal to minus 0, that is equal to 0, right? So now we can write this integral I in terms of t as integral. Here we have infinity, here we have 0. For y we can write minus t, and this is raised to n, and we have e raised to minus t, and for dy we can write minus dt, right? So now to neutralize this negative sign, let us interchange the limits, because we know that a to b f of say t dt is equal to negative of b to a f of t dt. So when we interchange the limits, then we put a negative sign before the integral sign, right? So we can neutralize this negative sign by interchanging the limits. So I is now 0 to infinity. We have minus t raised to n and e raised to minus t dt, right? Okay, now let us take this or we can rewrite this integral as 0 to infinity minus 1 raised to n t raised to n e raised to minus t dt. So now we can take this minus 1 raised to n outside the integral, and then we can write 0 to infinity t raised to n can be written as n plus 1 minus 1, right? And here we have e raised to minus t dt, right? So now we have written this integral in this form, and we can easily see that this integral is gamma of n plus 1. Now viewers, see gamma of n is defined as 0 to infinity t raised to n minus 1 e raised to minus t dt, right? So this is the Euler's integral. So gamma of n is defined like this: 0 to infinity t raised to n minus 1 e raised to minus t dt, right? And here we see that for this n we have n plus 1, right? And remember, n belongs to the set of natural numbers. So now this integral I is given by minus 1 raised to n, and here we have gamma of n plus 1, right? So the value of this integral is minus 1 raised to n gamma of n plus 1, where n belongs to the set of natural numbers. So viewers, we can also express this result as I is equal to minus 1 raised to n, and gamma of n plus 1 can be written as n factorial, right? Because when n is a natural number, then gamma of n plus 1 is equal to n factorial, right? So now we can write the value of this integral equal to minus 1 raised to n and factorial n, where n belongs to the set of natural numbers. So now let us quickly find out the values of these two integrals with the help of this result, right? So in this problem we have 0 to 1 log x raised to 4, and 4 is natural number, right? So the value of n is 4. So the value of this integral can be written with the help of this result. So we have minus 1 raised to 4, and then we have here 4 factorial, right? So minus 1 raised to 4 is positive 1, because this is even powers, and 4 factorial is 24, right? So the value of this integral is equal to 24. Now similarly we can find out the value of this integral. Here we have 0 to 1 log x raised to 10, and 10 is a natural number, right? So the value of this integral can be calculated with the help of this result. So we have minus 1 raised to 10, and here we have 10 factorial. Minus 1 raised to 10 is positive 1, and we have 10 factorial. So this is simply factorial 10, right? We can calculate the value of 10 factorial. Hello viewers, In today's class, we are going to discuss yet another important and very conceptual problem from integrals, right? So in this lecture, we are going to solve this integral using the concept of gamma function, right? So here we have to find the value of this integral from 0 to 1, and we have x log x raised to n, right? And remember here the logarithm is a natural log, right? So here the base of this log is e, which is the exponential number, right? So let us take this integral as I, and we'll solve this integral by making use of the concept of integration by method of substitution. So in this integral, the value of n, it belongs to the set of natural numbers, right? So this power n is a natural number. So in the first step, what we will do, we'll take a variable, say y is equal to a negative of log of x, right? So here I will make this substitution, right? So now when y is equal to negative of log x, then log x can be written as equal to minus y, and by definition of log, we can write x is equal to e raised to minus y, right? Okay, now let us differentiate x is equal to e raised to minus y with respect to y, right? So what we will get, dx over dy is equal to d by dy of e raised to minus y. So we have minus e raised to minus y, right? So dx can now be written as minus e raised to minus y, and here we have dy, right? Okay, now we'll change the limits. So here we see that the limits vary from 0 to 1, right? So when x is equal to 0, then here if we take x is equal to 0, then y tends to positive infinity, right? Because when x tends to 0, then log 0 tends to minus infinity, and here we have a negative sign. So we have y tends to positive infinity, right? And similarly, when x is 1, then we have y is equal to minus log of 1. So that is equal to 0, because log of 1 is equal to 0, right? So when x goes from 0 to 1, then y goes from infinity to 0, right? So now we can rewrite this integral I in terms of the new variable y. So now let us write I in terms of y. So we have here infinity, then we have 0 here, and x is replaced by e raised to minus y, e raised to minus y, and log x is replaced by minus y, right? So here we can write minus y, and we have the power n, and dx is equal to minus e raised to minus y and dy, right? Okay, now see, here we have minus y raised to n. So we can take minus 1 raised to n outside the integral, and then we have infinity, then we have here 0, and here we have e raised to minus ny, and then we have y raised to n, and then we have here a minus e raised to minus y and dy, right? Okay, now see, here we have an extra negative sign, right? Minus 1 raised to n we have taken outside the integral as such, and here we have an extra negative sign. So we can neutralize this negative sign by interchanging the limits, right? So we have minus 1 raised to n, so we can write 0 to infinity, because we know a property of definite integrals, that is a to b, f of x dx is equal to negative of b to a f of x dx, right? So when we interchange the limits, we put a negative sign before the integral sign, right? So here we have e raised to minus ny, then we have minus y, here we have minus y, and because the base are same, and here we have y raised to n and dy, right? So now we can write minus 1 raised to n, 0 to infinity, e raised to minus n plus 1, and here we have y, and then we have here n, and then dy, right? So now we have reduced this integral into this one by making this substitution, y is equal to negative of log x, right? Now we'll make another substitution here. It implies that we have to solve this integral by making use of the method of substitution twice, right? So now let us take another substitution. Say z is equal to n plus 1 y, right? So y is now z divided by n plus 1, right? And here we see that y varies from 0 to infinity. So when y is 0, then z is simply n plus 1 times 0, and here z is 0, right? And similarly, when y is infinity, then z is also infinite, right? And remember, here n is a natural number, right? So now let us differentiate z with respect to y. So we have dz over dy is equal to n plus 1, right? Because the derivative of y with respect to y is 1, and now dy can be replaced by dz divided by n plus 1, where n belongs to the set of natural numbers. So viewers, now let us express this integral I in terms of this new parameter or new variable z, right? So here we have minus 1 raised to n, then we have 0 to infinity, and when we take the variable z, the limits remains the same. So we have 0 to infinity, right? And here we have e raised to minus z, n plus 1 times y is z, and we have here y can be replaced by z over n plus 1, and here we have the power that is n, right? So here we have n, right? And dy can be replaced by dz divided by n plus 1, right? So now we have this integral. So let us simplify it. So we have minus 1 raised to n, and here we have 0 to infinity, e raised to minus z, we have z raised to n, n plus 1 raised to n, here we have dz, and here we have n plus 1 raised to 1, right? So now see, here the bases are same, so we can add the exponents. So we have minus 1 raised to n, 0 to infinity, then we have e raised to minus z, and then we can write z raised to n dz, and n plus 1 raised to n plus 1, right? So we can take it outside the integral. So we have n plus 1 raised to n plus 1, right? Okay, so now we have this expression, and let us apply the concept of gamma function to this integral. So now let us write this integral as minus 1 raised to n, n plus 1 raised to n plus 1. We have 0 to infinity, e raised to minus z, and z raised to n can be written as n plus 1 minus 1, right? Because this one and this one get cancelled. Why we have introduced here n plus 1? Because see, gamma of m is defined as 0 to infinity e raised to minus z and z raised to m minus 1 dz, right? So this is the famous Euler's integral, and this integral 0 to infinity e raised to minus z, z raised to m minus 1 is given by gamma of m, right? So if we compare these two integrals, then we can see that m can be replaced by n plus 1, right? So this integral now it takes the form gamma of n plus 1, right? So I can be written as minus 1 raised to n plus 1 raised to n plus 1, and here we have gamma of n plus 1, right? So viewers, the value of this integral is given by this expression, right? Now here we see that our n belongs to the set of natural numbers, right? So by definition, we can write gamma of n plus 1 is equal to factorial n, right? So we can replace gamma of n plus 1 by factorial n. So we have I is equal to minus 1 raised to n and n plus 1 raised to n plus 1, and here we have factorial n, right? So the final value of this expression or this integral is given by this expression, right? So now suppose we have to find the value of this integral 0 to 1 x log x raised to 4, then we can compare this integral with this one. So the value of n is equal to 4, right, which is a natural number. So the value of this integral can be obtained by putting n is equal to 4 in this result. So we have the value of this integral as minus 1 raised to 4, 4 factorial. Here we have 4 plus 1 5 and 4 plus 1 5, and minus 1 raised to 4 is plus 1. 4 factorial is 24 and 5 raised to 5 is 3125, right? So the value of this integral is now 24 divided by 3125. Now let us find out the value of this integral using this result. So this is 0 to 1 x log x raised to 3, and here if we compare this integral with this one, then the value of n is 3, right? And 3 is a natural number. So we can find the value of this integral by putting n is equal to 3 in this result. So the value of this integral is minus 1 raised to 3, 3 factorial, then 3 plus 1 4, then 3 plus 1 4, so we have 4 raised to 4, right? So minus 1 raised to 3 is minus 1, 3 factorial is 6, and 4 raised to 4 is 16 times 16, that is 256, right? So let us simplify it. So we have minus 6 over 256. So this is 2 3s are 6. Then we have 2 12s are 24, and here we have 8, right? So the value of this integral is minus 3 divided by 128. Hello viewers, in today's class we are going to discuss yet another important problem from integrals, right? And in this class we'll discuss this integral using the concept of beta function, right? So the beta function is also known as Eulerian integral of first kind, right? So here we have to solve this integral that is from 0 to 1, and the integrand is 1 minus square root of x raised to 8, right? So in this lecture we'll see a beautiful application of beta function to evaluate this type of integral, right? So let us start. So let us call this integral as I, right? So here what we will do, we'll make use of that method of substitution, right? So let us substitute square root of x as y, right? So y is now y square is equal to x, right? So let us differentiate both sides. So dy square is equal to dx, so we have 2y, dy is equal to dx, right? Now let us change the limits, right? So here x varies from 0 to 1. So when x is 0, then the value of y can be calculated from this relation. So y is equal to square root of 0, that is equal to 0. And when x is equal to 1, then the value of y is square root of 1, that is simply 1, right? So when x goes from 0 to 1, then y goes from 0 to 1. So now let us express this integral in terms of this new variable y, right? So now we can write I is equal to 0 to 1. We have 1 minus square root of x, which is replaced by y, and we have here the power 8, and dx is replaced by 2y dy, right? Okay, so now this 2 can be it can be taken out outside the integral. So we have 2, 0 to 1, 1 minus y raised to 8, and we are left with only y, right? So now we can express this integral as 0 to 1, and here we have y raised to 1. So y raised to 1 can be written as 2 minus 1, right? And 1 minus y raised to 8 can be written as 9 minus 1, right? So we have written this integral in this form in order to convert it into beta function. Now see, the beta function, that is beta mn, is defined by this integral, that is 0 to 1, and we have say x raised to m minus 1 and 1 minus x raised to n minus 1 dx, right? Where m and n are greater than 0, right? So this integral is known as beta function, or the Eulerian integral of first kind. And here we see that this integral is similar to this one, right? Except the variable. So here we have y and here we have x. And see, if we compare this integral with this one, then see the value of m is 2, right? So this is m, and here we have 1 minus x, here we have 1 minus y, and the value of n is 9, right? So we have now this integral, that is 0 to 1 y raised to 2 minus 1, 1 minus y raised to 9 minus 1 dy is equal to beta of mn. So here we have beta, m is 2 and n is 9, right? So now this integral I can be written as 2 times, here we have 2 a factor, and then we have beta of 2 comma 9, right? So now we know that an important relation between the beta function and the gamma function, beta mn, is given by gamma of m, then gamma of n, and divided by gamma of m plus n, right? Where m and n are greater than 0, right? So here we have m is equal to 2 and n is equal to 9. So using this relation, we can write beta 2 comma 9 as gamma of 2, gamma of 9, and then we have gamma of 2 plus 9, right? So now we can write this integral I as 2 times gamma of 2, and we know that gamma of n is defined as, that is gamma of n plus 1 is defined as n factorial, right, where n belongs to the set of natural numbers, right. So here, so when n belongs to the set of natural numbers, then gamma of n plus 1 is equal to n factorial. So here we have gamma of 2, right? So gamma of 2 can be written as 1 factorial, and then gamma of 9 can be written as 8 factorial, and in the denominator we have gamma of 11, and gamma 11 can be written as, here 1 factorial is 1, 8 factorial, and then gamma of 11 is equal to 10 factorial due to this relation, right. So now we can write 2 times 1 times 8 factorial. 10 factorial can be written as 10 times 9 times 8 factorial. 8 factorial and 8 factorial get cancelled. Here we have 2 5s are 10. So we have 1 over 5 times 9, that is equal to 1 over 45, right? So the value of this integral is equal to 1 over 45, right? Hello viewers, in today's class we are going to discuss yet another important problem from integrals, right? So in this class we'll solve this important integral using the concept of beta function, right? And beta function is also known as Eulerian integral of first kind, right? So we'll see a very beautiful application of beta function, how to evaluate this type of integrals, right? So let us start. So let us call this integral as I, right? So here we have the integral 0 to pi x square divided by square root of pi minus x dx, right? So here what we will do, we'll first make use of the method of substitution, right? So what we will do, let us first take in the denominator, we'll take pi as common, right? So we have pi 1 minus x over pi, right? So this is the first step. So now we can write it as 0 to pi. Here we have x square, and we can take square root of pi like this, and then we have square root of 1 minus x over pi, right? Okay, now let us rewrite this integral as 1 over square root of pi, and then we have 0 to pi and x square, and let us take this term to the numerator. So we can write 1 minus x over pi raised to minus half, right? Because this is square root, this is 1 over 2 power, so we can take it to the numerator. So this is minus 1 over 2. So now let us make the use of substitution method, and let us take y is equal to x over pi, right? So we'll take x over pi as y. So this implies that x is equal to pi y, right? And here we see that the value of x varies from 0 to pi. So we have x is equal to pi y. So dx is equal to pi dy, right? And we can change the limits accordingly. So when x is equal to 0, then the value of y can be obtained by taking x is equal to 0 in this relation. So we have y is equal to 0 over pi, that is equal to 0. And when x is equal to pi, then we have y is equal to pi over pi, that is equal to 1, right? So when x goes from 0 to pi, y goes from 0 to 1. So now we can rewrite this integral in terms of this variable y as 1 over square root of pi. Then we have 0 to 1, and x can be replaced by pi y. So we have pi y square, and then we have 1 minus y and raised to minus 1 over 2, and dx can be replaced by pi dy, right? So let us arrange the terms here. So we have 1 over root pi, and see here we have pi square and here we have pi, right? So pi square times pi is pi cube. We can take pi cube outside the integral sign. Then we have 0 to 1, and here we have y square, and then we have 1 minus y raised to minus half, and here we have dy, right? So now let us again rearrange this integral. So we have I, here we have pi cube, here we have square root of pi, which is pi raised to half. So now we can write pi raised to 3 minus half, and we have 0 to 1. Y square can be written as y raised to 3 minus 1, right? Because 3 minus 1 is 2, and here we have 1 minus y, and here we have power minus 1 over 2. The exponent is minus 1 over 2, that is the half minus 1, right? So we have written this integral in this form because we are going to use the definition of beta function, right? So the beta function is defined as beta mn as 0 to 1, that is x raised to m minus 1, 1 minus x raised to n minus 1 dx, right? So if we compare this integral with this one, then we see that the value of m is equal to 3 and the value of n is equal to half, right? So n is half. So now we have I pi raised to, this is 3 to the 6, 6 minus 1, 5. So we have pi raised to 5 by 2, and this integral is now written as beta, and here we have mn. So m is 3 and n is half, right? Now let us make use of one important relation between beta function and gamma function, right? Now see, beta of mn is defined as gamma of m multiplied gamma of n divided by gamma of m plus n, right? Where m and n are both greater than 0. Right, so here we have m is equal to 3, n is equal to half, and 3 and half are both greater than 0, right? So now due to this relation, we have pi raised to 5 by 2, and here we have gamma of 3, then we have gamma of half, then we have gamma of 3 plus half, right? So this is pi raised to 5 by 2, gamma of 3, gamma of half, and here we have gamma of 5 by 2. Sorry, here we have 3 to the 6, 6 plus 1, 7, right? So we have gamma of 7 over 2. So now let us write the values of gamma of 3 and gamma of 7 by 2, right? So gamma of 3 is equal to 2 factorial, right? Because we know that gamma of n plus 1 is equal to n factorial when n belongs to the set of natural numbers, right? Or when n is 0, then we have gamma of 1 is equal to 1 factorial, that is 0 factorial, that is equal to 1, right? So using this relation, we have gamma of 3 is equal to 2 factorial, which is equal to 2, right? And using an important relation, that is gamma of n plus 1 is equal to n times gamma of n. We can write gamma of 7 by 2 as 5 by 2 times 3 by 2 times half, and then we have gamma of half, right, due to this result. So now this integral I can be written as, here we have pi raised to 5 by 2, gamma of 3 is equal to 2 factorial, and here we have gamma of half, and in the denominator we have gamma of 7 by 2, and due to this result gamma of 7 by 2 is equal to 5 by 2 times 3 by 2. Here we have half, then we have gamma of half, right? So we know that gamma of half is equal to square root of pi, right? So these two terms get cancelled. So now we have pi raised to 5 by 2. 2 factorial is 2. Here we have 15 divided by 8, right? 5 3s are 15. 2 times 2 times 2 is 8. And we have pi raised to 5 by 2. 2 times 8 divided by 15, right? So taking this 8 to the numerator. So we have 2 8s are 16. So we have 16 times pi raised to 5 by 2 divided by 15, right? So the value of this integral is equal to 16 over 15 times pi raised to 5 by 2. So viewers, this is how by the application of beta function we can evaluate these kind of integrals. Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from integrals using the concept of beta functions, right? So in this lecture we are going to find out the value of this integral using the concept of beta function, right? So here we have to evaluate the integral 0 to 4, and the integrand is x raised to 4 times the square root of 16 minus x square, right? So let us call this integral as I, right? So let us start. So viewers, what we will do here, we'll make use of the method of substitution, right? So first we'll write this integral as 0 to 4 x raised to 4, and we'll take this 16 common like this, that is 16 1 minus x square over 16, right? And then we can take the square root of 16, and the square root of 16 is 4. We can take 4 outside the integral sign, right? So we have 0 to 4 x raised to 4, and here we have square root of 1 minus x square over 16, right? Okay, so now we'll make use of the method of substitution, and we'll take y is equal to x square over 16, right? So we'll introduce a variable, that is y, which is equal to x square over 16. So now we can write x square is equal to 16 y, and we can also write x is equal to 4 times square root of y, right? So taking the square root of 16y, we have 4 times square root of y, right? Okay, now let us differentiate both sides with respect to y. So we have dx over dy is equal to 4 times the derivative of square root of y with respect to y, right? So this is 4 times the square, the derivative of square root of y is 1 over 2 times square root of y, right? So this is 2 2s are 4, so we have 2 over square root of y, right? So now we have dx over dy is equal to 2 over square root of y. So now we can write dx is equal to 2 over square root of y and dy, or in other words we can also write it like this: 2 times y raised to minus half, and here we have dy, right? So for this dx we have 2 times y raised to minus half dy. So now let us change the limits. So here we have x is equal to 0, and the upper limit is 4. So when x is equal to 0, then we can find out the value of y from this relation. So y is 0 square over 16, that is 0. And when x is 4, we have y is equal to 4 square over 16, that is 16 over 16, that is equal to 1, right? So when x goes from 0 to 4, y goes from 0 to 1. So now we can write this integral in terms of y, right? So we have 4, then we have 0 to 1, and x raised to 4, right? See, x square is 16y. So we have x raised to 4 is equal to x square raised to power 2, and x square is 16y, right? And here we have square. So here we can write 16y raised to the power 2, and here we have square root of 1 minus x square over 16, that is equal to y. So here we have y. For dx we can write 2 times y raised to minus half, and here we have dy, right? Okay, now see, here we have 16 square. So 16 square is 256. So we can write 256 outside the integral sign, and we can also take this 2 outside the integral, and now we have 0 to 1, and here we have y square. This is y square, and here we have y raised to minus half. So here we have half, and then square root of 1 minus y can be written as 1 minus y raised to half, and here we have dy, right? So now the product of these three numbers is equal to 2048, and we have 0 to 1, and this is y raised to 2 to the 4, 4 minus 1, 3. So we have 3 by 2, and 1 minus y raised to half, right? Okay, now we'll write it like this: 0 to 2048, then we have 0 to 1, and see, y raised to 3 by 2. Now we can express 3 by 2 as 5 by 2 minus 1, right? So why we are writing this like 5 by 2 minus 1? In order to convert this integral into the beta integral, right? And here we have 1 minus y raised to 3 by 2 minus 1, right? So now we have written y raised to 3 by 2 as y raised to 5 by 2 minus 1, and half as 3 by 2 minus 1. So now see, the beta function is defined like this: beta mn. We can write it as 0 to 1, and here we have x raised to m minus 1, and 1 minus x raised to n minus 1 dx, right? So where m and n are greater than 0, right? So the Euler's first integral is defined like this: the beta mn is 0 to 1 x raised to m minus 1, and 1 minus x raised to n minus 1. So if we compare this integral with this one, then we can see that the variable is y here, the variable is x here, and it is not going to change it. And here m is 5 by 2 and n is 3 by 2, right? So comparing, we have m is equal to 5 by 2, and n is equal to 3 by 2, right? So now this integral I can be written as 2048, and here we have beta mn. M is 5 by 2 and n is 3 by 2, right? So now we have to calculate the value of beta 5 by 2 comma 3 by 2, right? And we know this relation, that is relation between beta function and gamma function, that is beta mn is given by gamma of m multiplied gamma of n and divided by gamma of m plus n, right? So the beta of 5 by 2, 3 by 2 is equal to gamma 5 by 2. Then we have gamma here 3 by 2. And then we have gamma of 5 by 2 plus 3 by 2, right? Now see, in the denominator we have gamma of 5 by 2 plus 3 by 2, right? So this is 5 plus 3, 8 over 2, that is gamma of 4, and gamma of 4 can be written as 3 factorial, right? Because we know that gamma n plus 1 is equal to n factorial, where n belongs to some positive integer, right? So here we have 3 factorial. 3 factorial is 3 times 2 times 1, that is equal to 6, right? Okay, now to get the value of gamma of 5 by 2 and gamma 3 by 2, we'll make use of one important relation, that is gamma of n plus 1 can also be written as n times gamma of n, right? So gamma of 5 by 2 can be written as 3 by 2 times half times gamma of half, right? Due to this result. So we have 3 by 4 and gamma half is square root of pi, right? So the value of gamma half is square root of pi, and gamma of 3 by 2 can be written as half times gamma of half, and that is half times square root of pi, right? So viewers, the value of this quantity is now 3 by 4 square root of pi, and here we have half square root of pi, and in the denominator we have 6, that is 3 factorial, that is 6, right? So this is 3 divided by 4 times 2 times 6, and here we have square root of pi times square root of pi, that is pi. So this is 3 to the 6, so we have 4 times 2 times 2, that is pi over 16, right? So now the value of this integral I is equal to 2048 times beta of 5 by 2, 3 by 2, and this is 2048 times pi over 16, right? So the value of this quantity is pi over 16. Now if we divide 2048 by 16, we'll get 128, right? So we have 128 times pi, right? So the value of this integral using the concept of beta function and gamma function is 128 times pi, right?